Several lessons ago, we spent a lesson considering linear inequalities. These were like linear equations, but with the equal sign changed to something like a less than symbol, or a less than or equal to, greater than or equal to symbol. We then also talked about solving systems of linear inequalities in the process, where we would have two or more linear inequalities working together. In this lesson, I want to continue on this theme of inequalities, but I want to start solving inequalities that involve x squared terms, not just linear inequalities. So we're going to call these quadratic inequalities, thanks to those x squared terms. Let's start talking about how one would see or visualize the solution set for just one quadratic inequality by itself. Here's the example I want us to start with. Graph the solution set for the inequality y is greater than or equal to x squared minus 10x plus 21. Now I want you to notice that the right-hand side is a quadratic expression since that x squared is there. So the boundary for this solution set is going to be a parabola. Remember, when we were studying linear inequalities, the boundary, so to speak, was a straight line, and we would break the plane into two pieces then based off of that straight line. Well, now with quadratic inequalities, the boundaries are actually going to be parabolas. So we'll draw that parabola as a boundary, and that will split the plane into a piece above and a piece below, so to speak. So, with that said, let's go back to this example now. What does this boundary graph, this boundary parabola, if you will, look like? Well, we can answer that question in a few different ways. First of all, because the sign on the x squared term is positive, I know that the parabola is going to be U-shaped, or if you will, it's going to go up. The ends will go up. Okay, so that's a start. We also see that the right-hand side of this inequality factors nicely as x minus 7 times x minus 3. And what does that mean about the intercepts of the parabola? We talked about this a couple lessons ago. They must be at x equals 7 and x equals 3. So if we just wanted to get a decent sketch of the graph, and we weren't real careful about it yet, we could draw this U-shaped parabola which goes through these two intercepts, x equals 3 and x equals 7. But what if we wanted to be more precise about where this graph is actually located in the plane? Well, there's one more special point that we might go look for. Do you have an idea what that is? That's right, it's the vertex. And to get the vertex, our best bet is to use completing the square as we did a few lessons ago. Now, can you remember how to do that? Well, let's try it here. Go back to the right-hand side of this inequality, x squared minus 10x plus 21, and try completing the square on those terms. Okay, let's do it together now and make sure that we did okay. I look at the x squared minus the 10x. I focus my attention on the 10 in order to complete the square. Do you remember what we do? We divide that by 2 first, always divide it by 2. That gives me 5. And then I square that 5 to give me 25. And 25 then needs to be added and subtracted from this expression. So instead of just x squared minus 10x plus 21, I'll have x squared minus 10x plus 25 minus 25 plus 21. Remember, plus 25 minus 25 is like adding 0, so it's like doing nothing. And then I put the 25, the positive 25, with the x squared minus 10x. And I group those together. X squared minus 10x plus 25 is exactly x minus 5 squared. And at the end of everything, then I have a negative 25 still plus 21, which is negative 4. So what I've done is I've replaced x squared minus 10x plus 21 with the equivalent expression x minus 5 squared minus 4 by completing the square. And now I know exactly where the vertex is. Can you pull it out of that information? It's going to be at positive 5, comma, negative 4. And now I can plot this parabola with much more accuracy. I know it opens upwards, I know where the vertex is, and I know where those two intercepts are. And if I plot that information and then carefully connect the dots, I'll see that the parabola looks like this. Now, let's say a few more things about the inequality. Remember, we were dealing with an inequality here, so we've got to think about how to solve that problem. All we've done up to this point is basically draw in the boundary. First of all, this inequality that we started with is a greater than or equal to inequality, not a strict greater than inequality. And that means, just as when we were studying linear inequalities, that I'm going to draw this boundary parabola as a solid line, if you will, as opposed to little dashes, okay? So the graph is going to be drawn solidly as opposed to using dashes to fill in the parabola. All right, if I had had a strict inequality so that this was just y is strictly greater than x squared minus 10x plus 21, then I would have drawn the parabola in a dashed fashion. Okay, now I've drawn in the boundary, and now I just want to shade in the part of the xy plane that satisfies y is greater than or equal to x squared minus 10x plus 21. Well, those are going to be a set of points in the plane, and all of those points that are on the parabola are the ones where we are equal to x squared minus 10x plus 21. So now I want to know where are the points that are greater than or equal to, or I should say more carefully, where y is greater than or equal to x squared minus 10x plus 21. Well, it turns out here that they're the points that are sort of above the parabola. And if you're not sure of this, let's use the same technique we used in the previous inequalities lessons. Let's pick one of the points, if you will, and check to see if it satisfies the inequality. If it makes the inequality true, then that point will be in the region that we will shade. So for example, it looks like 5, 0 is in this upper region that I'm claiming is the solution set, basically the piece that's inside the parabola, so to speak, and above it. Well, let's just check to see if 5, 0 makes the inequality true. I'm going to plug in x equals 5 and y equals 0 into the original equation. Well, and not equation, inequality. I got to be careful with that. So we had y is greater than or equal to x squared minus 10x plus 21. Putting 0 in for y and putting 5 in for x everywhere gives me 0 is greater than or equal to 5 squared minus 10 times 5 plus 21. And that's saying that 0 is greater than or equal to 25 minus 50 plus 21, or 0 is greater than or equal to negative 4. Now we have to ask ourselves, is 0 greater than or equal to negative 4, true or false? The answer is true. And that means that this point, 5, 0, is in the solution set. And therefore, I can take the region that contains 5, 0, which is bounded by the parabola, and just shade that whole region in. And so, the solution set of this thing really is that portion. Now, notice from the graph that we drew that the origin is not apparently in the solution set. It looks like the origin is sort of on the other side of the parabola, if you will, sort of below the parabola. Let's make sure, just to be on the safe side, that the origin is not in the solution set. Let's convince ourselves of that. And that means I would want to plug in x equals 0 and y equals 0 into the original inequality because the coordinates of the origin are 0 and 0. Okay, starting with y is greater than or equal to x squared minus 10x plus 21, plugging in 0 for x and 0 for y gives me 0 is greater than or equal to 0 minus 0 plus 21, because 0 squared is 0 and 10 times 0 is 0. And that gives me, after simplifying a bit, 0 is greater than or equal to 21. True or false? Well, that's definitely false. 0 is definitely not greater than or equal to 21. So the origin is not in the solution set. And that's a good thing because we believed that the origin was outside of it and that the solution set was this portion of the plane where all the points are above, if you will, the parabola. So to finish the problem, you simply shade in that piece that's above or inside the parabola, and that will be the solution set. Okay, let's look at a similar example now just to get some practice, because these can take a little bit of time and there are a few nuances with these examples. So let's try to get to a second one now just to make sure we're on the right track. Let's graph the solution set of y is strictly less than 3x squared minus 24x plus 53. Now notice this is a quadratic inequality. It's definitely an inequality. I see the less than symbol. And it's a quadratic inequality because of the x squared. See that 3x squared at the beginning of the right-hand side. Okay, now, first thing I want to do is draw in this boundary for the solution set. Well, it's going to be the parabola that corresponds to the right-hand side of that inequality. In this case, since the inequality is strict, since it's strictly less than, I'm going to draw that parabola with dashed lines, if you will, just to remind me that the parabola itself is not part of the solution set. Okay, so let's keep that in mind. We have to draw the parabola in a dashed fashion in this example. Okay. Next, I see that the sign on the x squared term is positive. So just like with the previous example, this parabola is going to open up as opposed to opening down. And now I'm going to suggest that we just try to find the vertex and sketch the parabola once we know where the vertex is. And just do a quick sketch. So to find the vertex, I need to do a completing the square. And this completing the square has a little bit of an extra twist to it. So let's do it together and let's do it step by step. The parabola is going to satisfy the equation y equals 3x squared minus 24x plus 53. Now you see that 3 that's hiding in front of the x squared. I need to factor that 3 out of both the x squared term and the x term. The 53 can actually just sit out on the end. So we're just going to leave that there for a second. But I'm going to rewrite this now as y equals 3 times x squared minus 8x and then plus 53. Remember, the 3 times the 8 is the 24. Now, I only want to focus my attention on the x squared minus 8x. In fact, if you want to put a hand over the 53 and a hand over that extra 3 and not look at them at all, that's fine by me. Just focus on the x squared minus 8x. What would I have to add to x squared minus 8x in order to make that a perfect square? Well, I would divide the 8 by 2 and get 4. I would square the 4 and get 16. So I want to add a 16 into the parentheses there so that I have x squared minus 8x plus 16 inside the parentheses. But you've added something now, so you must subtract something so that everything works out just fine. Now think about this. You added a 16, but there was an extra little 3 sitting out in front of the parentheses. That means that what you've really added is 3 times 16, which is 48. So I need to, on the end of this expression, subtract a 48 next to the plus 53. I put a 16 inside the parentheses, which was the same as really adding a 48 because 3 times 16 is 48. So I must subtract a 48 in order to make everything balance. And that means after I rewrite the x squared and so on as a perfect square, I'm going to have 3 times the quantity x minus 4 squared minus 48 plus 53, or y equals 3 times x minus 4 squared plus 5. Now, I know that was a complicated bit of completing the square, but it's probably the most complicated one you could ever see. So that was a good exercise to go through. Now let's read off the vertex. Well, you've got it in front of you. It's got to be at 4, 5. Notice that the 3 that's in front of the whole thing has nothing to do with the vertex. The vertex of the parabola is just at 4, 5. It's now pretty easy to sketch the graph of our boundary parabola. I just plot the point 4, 5 in the xy plane, and then I have a parabola that has to go up. And since the vertex is above the x-axis to begin with, there are no x-intercepts. So once you have the vertex and you know the parabola goes up, just draw it in. It's no problem. But remember one thing. in this example, that parabola has to be drawn in a dashed fashion because the inequality was strict. Okay, now, once I have my boundary parabola drawn in, if you will, I just need to shade in the solution set that corresponds to all the points where y is less than the 3x squared minus 24x plus 53. So here's the question to finish the example. Where is that solution set? Well, it's either in the part that's sort of above the parabola, if you will, or it's in the rest of it, which I'm going to call below the parabola. It's a bit of a stretch of the term, but it's really the part that would be below, if you want to think of it that way. Well, how do I know which of the two of those pieces is the solution set? Well, I'm going to do the same trick that I've done several times now with inequalities. I'm going to pick one special point that's in the plane, and I'm going to ask myself, is that point in the solution set or not? If it's in the solution set, then I shade the part of the xy plane that has that point in it. If that point is not in the solution set, then I ignore that part of the plane and I shade the other part. And what's my favorite point to pick? The origin. So I'm going to pick x equals 0 and y equals 0 and plug those into the original inequality and ask myself whether I get a true inequality or not. So the original inequality was y is less than 3x squared minus 24x plus 53. Plugging in x equals 0 and y equals 0 gives me 0 is less than 3 times 0 squared minus 24 times 0 plus 53. Now, why do I always pick the origin? Well, it's because it cleans up the arithmetic so quickly. Notice that the right-hand side becomes 0 minus 0 plus 53. And even I can do that arithmetic. That's just 53. So my inequality becomes 0 for the y is less than 53. Now we have to pause. Is 0 less than 53? Yeah, sure it is. And since 0 is less than 53, the origin is a solution of the inequality, which means I need to shade in the part of the plane that does include the origin. And once I do that, the final answer looks like this. Now, I'd like to solve one more such quadratic inequality by itself before we get to systems of inequalities. We haven't even done two at a time yet, but let's do one more solving of one quadratic inequality before we move to a system. Okay, here's the example I want us to look at. Graph the solution set of y is less than or equal to negative x squared plus 9x minus 20. Okay, let's say several things quickly, very similar to the examples we've already done. First, the inequality is a less than or equal to, not a strict less than. So my parabola boundary will be drawn in a solid fashion as opposed to dashed. Okay, so that's the first comment to make. The second comment is that the parabola in this example is now an upside down U. Did you notice that little minus sign in front of the x squared? That minus sign tells me that this parabola is going to be pointing down, that the ends of it will be pointing down. So I need to now sketch that parabola because it acts like the boundary for the solution set. Okay, let me just suggest that we try finding the x-intercepts of this parabola, assuming that it has some x-intercepts. Remember, it might miss the x-axis completely. And once we find the x-intercepts, we'll just make a quick sketch using those and the comments that I just made about the thing having to go down. Now, the x-intercepts. We have several tools for finding the x-intercepts now, and one of them we just saw in a recent lesson, the quadratic formula. So let's actually use the quadratic formula to solve the following equation for x, and that will tell us the x-intercepts of this parabola. Here it is. Solve by the quadratic formula the following. Negative x squared plus 9x minus 20 equals 0. Why don't you try that first, and then we'll get back together and do it together. Okay, plugging in our values for a, b, and c into the quadratic formula, here's what we're going to get for those x-intercepts of the parabola, or for the solutions of this equation. X equals negative 9 plus the square root of 9 squared minus 4 times negative 1 times negative 20, all over 2 times negative 1, because a is negative 1. And the other solution will be similar. X equals negative 9 minus the square root of 9 squared minus 4 times negative 1 times negative 20 over 2 times negative 1. Let me simplify these now quickly. These are very similar to what we did in a previous lesson. First, the first solution is x equals negative 9 plus the square root of 9 squared minus 4 times negative 1 times negative 20 over 2 times negative 1, which is the same as negative 9 plus square root of 81 minus 80 over negative 2, which is the same as negative 9 plus the square root of just 1 over negative 2, which is negative 9 plus 1 over negative 2, which is negative 8 over negative 2, which is positive 4, because those negatives will cancel. So one of the solutions here, i.e. one of the x-intercepts for my parabola, happens at x equals 4. The other solution then looks like the following. X equals negative 9 minus square root of 9 squared minus 4 times negative 1 times negative 20 over 2 times negative 1, which is the same as negative 9 minus square root of 81 minus 80 over negative 2, or negative 9 minus square root of 1 over negative 2, which is negative 9 minus 1 over negative 2. That's negative 10 over negative 2, which is positive 5. So the two x-intercepts for this parabola are actually pretty friendly. They are x equals 4 and x equals 5. And once I know that those are the two x-intercepts, and I know that the parabola goes downward, I can pretty much sketch the graph of this parabola very quickly. It's going to look something like this. Now, once I've done that, I just need to choose the portion of the xy plane, which is the solution set for the original less than or equal to inequality. It's either going to be the part below the parabola, or it's going to be the part sort of above the parabola, if you will. How am I going to figure out which one? Try the origin again. Plug in the origin and see if it makes the original inequality true. And when you do that, and I'll let you do it on your own, you're going to find that the origin does not actually make the original inequality true. So the origin is not in the solution set, and that means I want to shade in the part of the plane which does not include the origin in this case, and that's going to be the part of the plane which is basically below the parabola. Or some might say it sort of looks like it's inside the parabola. But of course, it's not really inside it because it goes on forever in the sort of negative infinity direction. But the point is, the solution set would look something like this, with this shaded region inside and below that parabola. Now, I want to turn a corner to solving systems of two quadratic inequalities at the same time. So we've dealt with systems of linear inequalities in the past, and if you remember, the idea was we would draw in the boundary graphs, we would shade in the parts of the plane which represented the solution sets for each individual inequality, and then we would find the intersections, the intersection points. And that intersection would be the final solution set of the system of inequalities. Well, guess what? It's the same game here with quadratic inequalities. We're going to draw in the boundaries. We're going to shade in each individual solution set. We'll look for the intersection, and the intersection will be the final answer. So let's do the following example. Solve the system of inequalities. Y is greater than or equal to x squared minus 8x plus 7, and y is less than or equal to negative x squared plus 5x. Okay, let's look at the first inequality first, and we see that it is going to have a boundary which is the parabola given by y equals x squared minus 8x plus 7. Now, I could go after that with the quadratic formula. We could do all kinds of things, but that actually factors pretty quickly as x minus 7 times x minus 1. So I know that this equation is giving me a parabola with two x-intercepts. One of them is at positive 7, the other one is at positive 1, and I know that it's a U-shape going up because the x squared term had a positive 1 in front of it. So that can be sketched very, very quickly in this way. Now notice also that this was a greater than or equal to, so that parabola is being sketched in a solid way as opposed to in a dashed way. And the portion of the plane which is the solution set of this greater than or equal to inequality is going to be the part that's above or inside of the parabola, however you want to think about that. So you can shade that in pretty quickly. If you don't believe me, pick a point in that region and just confirm that it makes the original inequality true. Now, I could then go to the second inequality that was in the problem and sketch its boundary parabola. In this case, that parabola will be given by y equals negative x squared plus 5x. Now, that's a parabola that's going to open downwards because of the negative that's in front of the x squared. And I know how to factor negative x squared plus 5x pretty quickly. That factors as x times negative x plus 5. I've just factored there using the greatest common factor. And if I look at y equals x times negative x plus 5, I can quickly see the two x-intercepts that are going to occur on this new upside-down parabola. They're going to happen at x equals 0. That's from the x term, the first factor in the factorization. And the other one will happen when negative x plus 5 equals 0, and that happens when x is positive 5. So I have two x-intercepts for this second parabola. One is at 0, and one of them is at 5, and the thing opens downward. So I can plot those two x-intercepts and plot my parabola that goes through them, and I can sketch that boundary on the same set of axes as I sketched the first inequality as well. Now, since this second inequality was a less than or equal to inequality, I want to sketch this second parabola also with a solid rather than a dashed line, so to speak. And so I'm going to do that for the boundary, and then I need to ask, where is the solution set for this second inequality? Well, since I want y to be less than or equal to this quadratic, it turns out that the solution set is the part of the xy plane which is sort of inside or below this parabola. So you can see that here. And if you don't believe it, try a point in the plane and check to make sure that that really is the solution set. Now, your graph might be getting a bit messy. You got two parabolas, you got pieces floating around that have been shaded in. What's the solution of the original problem, of the original system? And it is the intersection of these two shaded regions. So all you want to keep as the final answer is the intersection part, the part where the two regions overlapped, and that will be your final answer. Okay, I'd like to do one more example quickly as we close today, and I want to start by seeing if you can actually graph it yourself. So here's the example. Solve the system. Y is greater than or equal to x squared, as well as y is greater than or equal to x minus 4 whole thing squared. Well, thankfully, we can actually draw both of those boundary parabolas very quickly. By now, you and I have seen y equals x squared and its parabola quite often. So we should be able to draw that parabola very quickly. Its vertex is right at the origin, and it opens up. What does the graph of y equals x minus 4 squared look like? Well, that's just the graph of x squared, but it's been shifted now 4 units to the right. So these two parabolas both sit on the x-axis, and they just look like carbon copies of one another, one shifted 4 units away from the other. Now, I need to shade the solution sets of these two inequalities, both of which are greater than or equal to. So they are y is greater than or equal to the x squared, and y is greater than or equal to the x minus 4 squared. And if you've been building a bit of intuition, you might guess that the two portions of the plane, which are the solution sets of each of those two inequalities, are exactly the pieces that are above or inside each of those two parabolas. And if that was your guess, then you would be exactly right. So we shade in those two pieces, and now we need to ask ourselves, but what's the final answer to the original system of inequalities? And the answer is, again, the overlap. So the final answer here is this sort of middle portion that we get after we draw in or shade inside both of those parabolas. Well, next time I want us to start talking about some very famous quadratic equations, which are connected with some interesting graphs called the conic sections. They've actually been studied for over 2,000 years. And I look forward to talking with you then.